My name is Bob Van Sickle. I am one of 3 founders and president of THOR Systems. We manufacture surge protection. These products have evolved and developed over 30 years of direct experience with 7 companies who manufacture power quality products: Power Distribution, United Power, Delta PLC, Innovative Technology, Danaher, Cont Technology, and Joslin. It is our objective to redefine product value in the marketplace, providing uncompromising product performance and exceeding expectations for all with whom we conduct business. We appreciate the opportunity to make this power quality surge protection presentation, which will provide the information for correctly applying, effectively specifying, and accurately sizing surge protection for specific applications. History began with the first generation TVSS, developed throughout 15 years spent at United Power Corporation, which was a great learning experience. The second generation of TVSS was developed at THOR Systems, requiring 8 months during startup. These all-new state-of-the-art product was manufactured for only 3 years. The third generation surge protective devices, SPDs, required a total redesign of our entire product line, which took 1 full year, including the new UL 1449 3rd edition testing. This major effort was driven by headwinds of change. We'll discuss that a little later. Our focus and culture: to be a technology leader, providing a hybrid design featuring performance, full surge-rated products, utilizing stack tracks, which defines our heavy copper, low impedance, parallel surge path design, which is used to divert transient energy away from protected equipment. We offer modular designs for highest level of surge protection, typically applied at service entrance and main distribution locations, and non-modular designs for lower ampacity distribution, sub-distribution, and branch circuit applications. We use advanced applied technologies and innovative features to enhance our products, as well as anticipate the needs of our customers. We train and promote correctly sizing surge protection for each specific application. This presentation will begin with our second generation products, continuing to the events leading to the development and introduction of our third generation of products. Design philosophy. This image shows THOR Systems' original second generation products. The hybrid design components are: first, silicon avalanche diodes, SADs. The SAD is an ideal suppression element. Its fast turn-on speed increases system longevity. It is a shock absorber to the MOV. The negatives: low power capacity and high cost. The second component is a large block 34mm square dual disc metal oxide varistor rated at 80 Ka. Each individual MOV is fed by an 80 Ka surge rated fuse. The third component are filter capacitors. They suppress EFI, RFI high frequency noise, reducing data errors, lockups, and reboots, which are costly to automated manufacturing and processing operations. All hybrid components are interconnected with stack tracks, which provide parallel low impedance surge paths which divert transient energy away from the customer's critical equipment. Design philosophy continued. Component design concepts. The THOR design philosophy has always been based on a small number of large block MOVs. The component of choice was a 34mm square dual disc MOV rated at 80 Ka. Each MOV is paired with a 80 Ka surge rated fuse, which provides the ability to deliver 100% of the surge rating. Many competitors provide a large number of small 18mm MOVs. 7 to 14 small MOVs are required to supply 80 Ka. The problem with applying large numbers of small MOVs is cascading failures. Which small MOV is the first to fail? How do I know that? The one with the lowest impedance, which is the best performer. Which is the next to fail? The next best performer. See the TVSS assembly image. 6 small MOVs have failed. 2 were vaporized. This is why THOR Systems does not use small MOVs. Catastrophic failures, the headwinds of change. To this point, we have been discussing THOR's second generation TVSS. The products were less than 3 years old. The entire product line was abandoned. The headwinds of change were brought on by a number of catastrophic end-of-life TVSS failures. Introduction: the gear guys decided to enter the TVSS market with their own brands. Square D, Cutler-Hammer, Siemens, and GE acquired TVSS products. They value engineered the TVSS, integrated in switchgear, direct bus mounted. Having large sales organizations with established distribution provided a number of facility installations in a short period of time. Then the problems began. Catastrophic end-of-life thermal runaway with arc flashes which caused collateral damage resulting in facility shutdowns. A number of these arc flash-induced system shutdowns occurred, shutting down hospitals, manufacturing facilities, 911 offices, automated processing operations, and a number of other critical applications. These events prompted us to write a white paper, Concerns of TVSS Integral to Switchgear and Panel Boards. The gear manufacturers claim they will simplify TVSS specifications. The reality is they specified a sole source, low-end TVSS, for which the customer paid a higher price as the TVSS was integrated in the gear and not separately detailed or evaluated. The next claim, direct bus mounting TVSS, provides lower impedance and improved performance. Again, the reality is direct bus mounting provides a much higher risk of collateral damage, contaminating the customer's electrical distribution and ultimate critical system shutdowns. Serviceability is also a serious concern with arc flash concerns. Failures continued. No one wanted to talk about these events. See the top circled left-hand photo. This is an event you don't want to have to explain to your customer. Surge protection, end-of-life, thermal runaway, catastrophic failure, causing arc flash, resulting in system shutdown. End users had lost services. Manufacturers just fix it and move on. The increased frequency of power quality events drove the realization additional fail-safe testing was necessary. Switchgear manufacturers deal with safety every day. What did they have to sell? Coordination. They took TVSS products without proper testing, integrated it into their core products without coordination, then wondered why they had problems. Square D took the lead position. A lobby was formed. They went to UL requesting additional fail-safe testing, relating we have to implement new testing very quickly, a major additional testing in a month or so. Think through this process, as it may have major impact on future product design, cost, and the manufacturing processes. The lobby suggested a revision to the existing UL 1449 second edition, which has been in effect since August 1996. The time was September 2006. The existing UL standard, which at the time was 10 years old, typically a standard lasts 10 to 12 years. The lobby wanted a quick solution, modify only one test, defined as an abnormal limited current test. which raises the voltage above the MCOV, the maximum continuous overvoltage rating of the device being tested, holds the voltage elevated, and runs limited current test. See photos. Upper right is Cutler hammer, bottom right center is square D, and the bottom left is GE. All have direct bus mounted TVSS. Failures continued. We, as well as our competitors, knew the UL 1449 third edition had been approved and was going into effect September 2009. This was 3 years away. We suggested UL bring the third edition forward by 2 years, giving all manufacturers 1 year to prepare for testing. Manufacturers would test one time for all new changes in the third edition, which included the revised fail-safe testing plus a number of additional revised tests. Our request was denied, as a number of our competitors were requesting to be tested the next month, but test only for the 2.5 revision. THOR considered the 2.5 revision a band-aid. We stopped manufacture, redesigned the entire THOR Systems product line. Every design was changed, every printed circuit board, every enclosure, all sub-assemblies. It took 11 months. THOR Systems was the first SPD manufacturer to pass UL 1449 third edition, a full 2 years before the mandated effective date. Review why not integral TVSS and SPDs. First, collateral damage. SPDs inside switchboard can cause ionized gas, thus arc flash, causing system shutdowns. Second, serviceability, having arc flash concerns. Next, low performance. Low-end, undersized products using fuse links, thermal cutouts, and undersized fusing, all of which limit the level of protection. Next, inflated cost. SPD's cost hidden in the electrical distribution equipment. See photos showing direct bus mounted SPDs. Square D, 3 small modules, and GE, a single small module. Failures continued. UL 1449 second edition abnormal limited current test included 8 different test levels, 5 amps being the maximum. THOR Systems using 34mm large block MOVs, having a large surface area, radiated the heat without failing. Many competitors use small 18mm MOVs encapsulated in sand or epoxy, could not dissipate the heat. They had to get offline, i.e. fail. The UL 1449's 2.5 revision changed from 5 amp maximum to 10 amps plus 100 amps plus 500 and 1,000. There was not a choice. Each TVSS must run all abnormal limited current tests and fail safe. There are 4 quick, easy solutions available to all manufacturers. First, undersized fusing. Second, thermal cutouts. Third, fuse links. Fourth, encapsulation in silica, sand, or epoxy. All 4 of these solutions increase the potential to fail prematurely, leaving critical systems equipment unprotected. We were on the UL Advisory Board and knew the UL 1449 third edition had been approved and was going into effect September 2009, 3 years later. This all came to a head in September 2006. The solution the TP MOV. The thermally protected MOV, a TP MOV, was developed by Faraz Shamit to assist in eliminating the failure characteristics of metal oxide arresters. The TP MOV provides full surge rating with a fail-safe design. We have been buying our fuses and working with Faraz Shamit for many years at United Power and THOR Systems. The power quality industry knew catastrophic failures were occurring. No one yet had a solution. Faraz was working on a new design, which developed an encased MOV defined as a thermally protected MOV, a TP MOV. Removing its cover exposes the blue 34mm square single disc MOV, rated at 50 Ka. Faraz reduced the cross-sectional area of one leg, which was soldered to the single disc. This reduced area generated the necessary heat to desolder the leg in time-related overloads. A double offset was added to the thinned leg, which created a natural spring. This thin leg assured thermal separation. As the leg moved away from the disc, the coil spring-loaded phenolic shutter, which was captivated under the leg, moves upward, becoming an isolation barrier, an arc shield, which assured fail-safe operation at all UL abnormal testing levels, yet maintained the ability to survive a 50 Ka transient event. The TPMOV has two modes of status indication. Physical indication: two pins on the spring-loaded shutter protrude through two apertures in the cover top. Remote indication: the shutter operates a microswitch providing form C contacts within the cover. The TPMV became the building block for THOR Systems modular and non-modular SPDs. Note: the UL 1449 3rd edition replaced transient voltage surge suppressor, TVSS, with surge protective device, SPD, now the latest surge protection product description. Performance limiting solutions. These pictures of surge protection competitors show a number of performance limiting elements to take a failing SPD offline. These elements are undersized fusing, fuse links, thermal cutouts, encapsulation with sand or epoxy, which contains cascading failures. Review of the photos. Figure 1 shows fuse links plus thermal cutouts, 80 Ka SPD with 9 Ka cutouts, plus sand encapsulation. Figure 2 uses epoxy encapsulation, shown failed. Figure 3 uses fuse links plus sand encapsulation. Figure 4 uses undersized fusing, 80 Ka SPD with 20 Ka fusing. Figure 5 uses sand encapsulation. Figure 6 shows fuse link failed open plus epoxy encapsulation. Figure 7 shows undersized fusing, 80 Ka SPD with 20 Ka fusing, plus sand encapsulation. All these elements promote premature failures. Introducing our third generation of products. Every design, printed circuit board, and enclosure was changed, providing unique solutions and offering an array of world-class products, bringing a new level of performance to the surge protection market. Our third generation products were a strong response to the unique challenges presented by UL 1449 2.5 revision and the 3rd edition, while maintaining the ability of delivering full rated surge protection to the customer. This development strengthened and expanded our product offering. Optimizing performance, quality, durability, and end-user value were our key design parameters. The new product development set the pace of change rather than reacting to change. THOR Systems was the first manufacturer to have successfully completed UL 1449 3rd edition testing 2 full years before the mandatory compliance date. Tile architecture is used for both modular TSR, field replaceable multi-tile designs, and TSN, non-field replaceable single tile designs. THOR Systems' new products outpaced its peers across every metric: design, performance, packaging, quality, and value. Our 3rd generation development was an ambitious, exciting undertaking, made more challenging by the fact we did not compromise the ability to deliver the full surge-rated protection. Its development took shape and ever more clearly as we completed the design platforms, system configurations, and product testing. Modular TSR products. THOR's 2nd and 3rd generations of modular TSR surge protection are shown. Their design features: hybrid 2 and 3 tier designs, multi-layer printed circuit boards, heavy copper bus structure using 1/4 by 1/2 inch bus bars and 1/2 inch hex bars. 3rd generation design changes: thermally protected TPMOVs replaced MOVs. Multi-tile design printed circuit boards replaced single base printed circuit boards. Application and equipment criticality defined using a 3-tier industrial or 2-tier commercial SPD design. Design philosophy: TSR modular copper bus structure. Left-hand image shows a TSR modular backpan assembly showing its heavy copper bus structure rated at 50, 100, and 150 Ka per mode, with a 60 amp fuse disconnect provided with surge-rated fuses. The right-hand image shows a TSR backpan assembly rated at 200, 250, and 300 Ka per mode. The center image is a number 6 AWG rope lay low impedance wire, which has 7 twisted groups of 37 strands per group, providing 259 strands, versus a number 6 AWG THHN with 19 strands. The increased strand count increases the wire surface area, which reduces the impedance at 40 to 50 kilohertz, the frequency of transient events, improving SPD performance 6 to 12%. The TSR modular multi-tile design features individual field replaceable modules. Each module has very bright green and red LEDs used for status indication. Green LED illuminated indicates operational online. Red LED illuminated indicates a component failure. Form C contacts will also be operated. Each module has a numerical code, which is the maximum continuous overvoltage rating, the MCOV of the device, and a color code also based on MCOV. Example, red is for 320 MCOV, purple is for 150 MCOV. As these modules are field replaceable, we were concerned the color and numerical code may be overlooked. This concern prompted the implementation of a pin and sleeve design. 5 apertures, 4 of which will be soldered shut closed, spaced around one of the 2 mounting bolts, and a steel pin is set for proper orientation to assure the correct module will be installed for the specific voltage configuration of the application. StackTrax defines the heavy copper multiple parallel low impedance paths used to direct transient energy away from protected equipment. The TSR modular SPD uses multi-tile design. Shown are 7 individual 300 Ka tiles arranged in a defined pattern to be assembled on the modular base structure. The configuration shown is for a 3-phase Y 4-wire plus ground. Shown is a 3rd generation TSRI 200 modular SPD. The backplane assembly has 3 field replaceable modules removed to show the solid copper bus structure. The TSRI 3-tier industrial design provides life of the installation warranty. The TSRI industrial and the TSRC commercial modular SPDs rated 50 to 300 Ka per mode are recommended for service entrance, main distribution applications, typically a higher ampacity, 400 to 6,000 amps, where protected equipment criticality is a vital concern. Options shown are integral fuse disconnect having surge-rated fuses and an industrial 3-tier TSRI modular SPD. These are 3 3rd-generation TSN non-modular SPDs. They are compact, high-performance SPDs with clear covers. UL 1449 4th edition listed. The TSN product ratings are 50, 100, and 150 Ka per mode, or 100, 200, and 300 Ka per phase. These TSN SPDs are typically applied at distribution, sub-distribution, and branch circuit panels, typically lower ampacity applications, 30 to 800 amps. These 3 non-modular products are available in 2 configurations. A TSNI industrial is a 3-tier hybrid design using SADs, TPMOVs, and filter capacitors. The TSNC is a commercial, is a 2-tier hybrid design using TPMOVs and filter capacitors. The TSN SPDs are pre-wired with low impedance wire. The TSRI uses rope lay and the TSRC uses MTW. All TSN enclosures are NEMA 4X rated, utilizing transparent covers which provide the means for the customer to see firsthand the features, workmanship, and the design put into these products. This is a TSNI non-modular industrial design. It is a 3-tier hybrid single tile design, which provides a life of the installation warranty. It includes silicon avalanche diodes, SADs, TPMOVs, and filter capacitors. These components are placed in close proximity to each other and interconnected using StackTrax low impedance parallel diversion surge paths. StackTrax provides the means to condense the product size, which increases overall system performance. All manufacturers can buy heavy copper. Why don't they? First is cost. Second, less than 5% of the printed circuit board manufacturers can produce these heavy copper printed circuit boards. Heavy copper is a good conductor of electrical current. It is also a good conductor of heat. During the PCB plating process with conventional plating equipment, the plating material cools and puddles. Heavy copper plating requires specialized, very high heat equipment. These heavy copper multiple parallel surge paths are a key element in providing improved surge suppression performance. These are our 3rd generation product options. Figure 1 is a TSR modular extended EFI RFI filter. Figure 2 is a TSR modular 3-tier industrial design with 15,000 watt SADs and filter capacitors. Figure 3 is a TSR modular integral fuse disconnect. Figure 4 is a TSN non-modular surge counter, which is field programmable. Figure 5 is a multifunction relay for monitoring phase loss, over and under voltage detection with time delay contacts. Figure 6 is a TSR modular surge counter. Figure 7 is a TSN 3-tier hybrid industrial design with 15,000 watt SADs. Modular and non-modular industrial 3-tier SPDs provide life of the installation warranty. This is a 3rd generation application guide 09, which is a review of the topics we have discussed. Figure 1 is a TPMOV fail-safe design. Figure 3 is a hybrid design utilizing SADs, TPMOVs, and filter capacitors. Figure 6 is a modular design TSR 50, 100, 150, and 200, 250, and 300 per mode. Figure 8 is modular TSR backplane assembly showing solid all-copper bus structure. Figure 9, electrical EFI, RFI high-frequency noise, which causes data errors resulting in lockups, restarts, and reboots. Figure 10, modular TSR extended filter for suppressing high-frequency electrical noise. Figure 11, schematic showing SADs in parallel to TPMOVs and filter caps. Figure 19, graph showing large block 34mm TPMOVs have 100 times the pulse life of 20mm MOVs used by some competitors. Figure 17, rope lay wire is a low impedance connection wire. Figure 12, non-modular designs, TSN 50, 100, and 150 Ka per mode. Figure 13, all surge protection components are interconnected by stack tracks, which provides low impedance surge paths. Power quality problems. External sources are a high or low percentage of problems. Examples are lightning, utility grid switching, traffic accidents, ice and snowstorms taking down transmission lines, contractors mistakenly cutting underground wires. Many people believe they are a high percentage of the problems. Typically, their magnitude is higher, however, the frequency of events is low, less than 20%. The power quality industry relates 80% of the problems are caused from within the facility. What causes facility-generated problems? Electrical system demand changes. Having inductive or capacitive components, which they all do. Press the start button on an induction motor. The coils magnetize, the motor spins up. This is not a transient event. If anything, it's a sag. The problem occurs when the stop button is pressed. The magnetic field collapses, the energy flows back into the distribution system. This is a transient event that happens continuously. The types of failures. First, catastrophic failures. Immediate equipment failure, 98% of the time showing no visual damage. Second, degradation over time. The system or components fail seemingly without cause. Think of water dripping on a concrete floor, which is a slow erosion of the concrete. Transients are a constant degradation of the electrical insulation inside an integrated circuit. Third, system disruptions. High-frequency electrical noise, EFI, RFI, cause unexplained elusive lockups, data errors, and restarts. which are very disruptive and costly to automated systems and manufacturing processes. Protected equipment history. In the past, small logic chips had 50 transistors. They had 0 to 5 volt DC operating voltage, which changed to 0 to 3 volt DC, and now is 0 to 1 volt DC. Why these changes? To provide faster settling time, which improves performance. Second, reduced voltage potential promotes a more condensed package, plus improved manufacturing techniques further condense the chip size. Now that same chip size can have thousands of transistors, improving processing speed, reduced costs, providing more affordable controls, which expanded applications, i.e., process control, computers, printers, HVAC, automated manufacturing. Older technology, linear power supplies, were large, expensive, having big magnetics and capacitors. Engineers were tasked to develop an improved, smaller, more efficient, and affordable replacement solution, which was the switch mode power supply, which improves speed, regulation, cost, size, and efficiency. The new technology power supply brought many advantages. However, without the large magnetics and capacitors, it provided no buffer whatsoever to the far more sensitive and vulnerable electronic controls, which have now become commonplace across industrial, commercial, and residential applications. Now, super-sensitive electronics have no protection. In the past, surge protection had been used in critical applications. Today, there is no applications that would not benefit from surge protection. Not one. This is a grounding application guide. It is a consolidation of white papers which were published in a number of technical magazines. This application guide addresses grounding issues. Surge protection will not perform correctly without proper ground bonding. See the pictorial drawing on the top and a schematic on the bottom. Both show examples which address proper ground bonding, all to the same potential. Tie every grounding system component to the same potential, including the data and communication grounds. The grounding system components. First, service entrance ground. Second, driven ground rods. Third, building structural steel. Fourth, perimeter ground ring. Fifth, steel and copper pipes. Sixth, concrete rebar. 7, buried ground plates. 8, data telecom grounds. 9, SPD and TVSS grounds. Critical applications are recommended to be less than 5 ohms and industrial applications less than 10 ohms. Grounding must be properly addressed to assure maximum surge protection performance. Ground testing. We use and recommend AEMC clamp-on ground resistance testers, models 3711 and 3731, with added memory and alarm functions for measuring and verifying grounds. This is a site risk assessment. Where should you apply surge protection? How do you size surge protection for a specific application? We've been asked this question many times. The answer is a THOR site risk assessment, which defines 7 susceptibility factors used to recommend and correctly size surge protection for specific applications. These factors are: first, ampacity of the application. Second, geographical location, which uses 2 maps. Bottom left-hand side is an isokinetic map, showing the average number of storm days per year. On the right-hand side is a ground flash map, which shows the average number of air-to-ground strikes per square kilometer. Third is the system voltage. Fourth is the voltage configuration. Is it a Y, or delta, or single phase. Number 5, short circuit current rating, the SCCR, at the point of SPD installation. It may be on the riser diagram. If not, take the full load amps and divide by 0.055, which assumes 5.5% impedance. This answer will be very close to the SCCR requirement. Number 6, SPD location, service entrance, distribution, subdistribution, or branch panel. Number 7, criticality of the load, a number between 3 and 10. Most critical is 10. 7 different applications can be done on one spreadsheet. Totals are calculated by the spreadsheet. Then see Table B showing the numerical total related to the recommended Ka surge rating per mode of the SPD and its available product series. This is how we recommend sizing surge protection for various applications. Modes of surge protection. How many modes are there in a 3-phase Y? See the schematic. There are 3 ABC to ground, plus 3 ABC to neutral, plus 1 neutral to ground equals 7 modes, plus 3 line to line equals 10 modes. How many modes are required to have surge protection elements? Some competitors say 10 modes. See the vector diagram. The 3 phases A, B, and C across the top of the triangle, and a single point at the bottom, which is neutral or ground. Which modes offer the lowest clamping levels? The modes having the lowest MCOV rating. 7 modes is the correct answer, as they have the lowest MCOV rating. 3 line to ground, plus 3 line to neutral, plus 1 neutral to ground equals 7 modes. An example. Specifications require 150 Ka rating per mode, which equals 300 Ka rating per phase. THOR 7-mode SPD versus a competitor's 10-mode SPD. THOR provides 150 Ka line to ground plus 150 Ka line to neutral equals 300 Ka per phase. Some competitors offer 10 modes. 100 Ka line to ground, plus 100 Ka line to neutral, plus 100 Ka line to line equals 300 Ka per phase. The THOR Systems 7-mode SPD provides 50% more surge protection in the modes that matter. At service entrance, most all transient events are line to ground. Within the facility, transient events are typically line to neutral. 7 modes in a Y-configured electrical system is the correct and most effective surge protection solution. The 10 mode is marketing propaganda, as the vector diagram clearly shows. A case study. Commercial Machine Company, a metalworking machine shop located in Richmond, Virginia. They were experiencing continuous, serious service issues, controllers and logic card failures. 2 main spindle motors failed. Both were less than 5 years old. Continuing restarts and reboots were causing machine downtime. Bob Jones, the business owner, asked for a site survey. We requested expense history and were provided with 32 months of prior cost history. Each invoice was reviewed by us and the business owner to confirm they were relative to poor power quality issues being experienced. These invoice reviews established a service downtime cost per month. THOR recommended installing surge protection at service entrance and panel boards feeding CNC equipment and the electrical welding department. The incoming communications and data lines should also have surge protection. The installation will include correction of identified ground bonding issues. The total investment was $13,840. The return on investment, the ROI, was 5.92 months. 40 months after the installation, we did a case study revealing one electrical issue. One module in the service entrance SPD had failed, which was replaced at no cost. A recap. Case study was done after 40 months, minus 6 months payback. The remaining 34 months times $2,336 savings per month based on their actual cost equals $79,424 of profits, which they're still collecting every day. Another manufacturing application, Old Dominion brush. Commercial Machine and Old Dominion Brush had business sharing relationship, and their owners had a close personal relationship. Commercial Machine had related their success after installing surge protection. Old Dominion bought a new CNC laser cutting machine. 2 months passed. The laser was down. Main controller had failed. Controller was replaced, costing $15,000, which they related to Bob Jones, who asked, "Have you contacted THOR Systems about surge protection?" Their answer was, "Not yet, but we're going to consider it." 2 more months passed. The new main controller failed, was replaced again, another $15,000. THOR Systems got a call the next day. We installed surge protection for Old Dominion Brush's entire facility. The cost was $27,203, including installation, now running over 5 years without any power quality issues. Surge protection is the least expensive insurance anybody can ever buy. It's a matter of convincing them it works. Identify and realize profit opportunities. This trifold was created at the request of facility managers who were convinced adding surge protection would improve their operations. However, the senior management, the CEO, CFO, will not approve the expenses. Can THOR Systems help provide the understanding and cost justification for the investment? We believe the answer is yes, by providing the following information to senior management. Who is being affected by poor power quality? The company, its owners, its staff, and its customers. The problem: United States industry spends over $200 billion a year. This cost by sector: commercial businesses, 73%, 14.9 million businesses. Industrial business, 25%, 1.6 million facilities. Inexpensive components cause large financial losses. Financial logic cards and controllers, equipment down, waiting on service. System lockups, reboots, and restarts. Logic cards and controller failures cause production and automated process downtime. Overtime expense to make up for lost production time. Customers' cost of poor power quality. We recommend looking at 2 categories in your own budget. Category 1, maintenance expenses, on the following items: switchgear and electrical distribution, emergency and mission critical equipment, motor controls, rewinds and replacements, building maintenance, lighting control systems, telecommunication equipment, office equipment, computers, servers, printers and copiers, elevators and escalators, security, fire detection and suppression, HVAC, chillers, and UPS systems. Category 2, miscellaneous expenses, record the cost for lost operating efficiency, machines are down, shortened equipment longevity, system availability, equipment is down, waiting on parts and service, late deliveries, unnecessary equipment lockups, reboots and restarts, material losses caused by process interruptions, increased inventory to bridge these interruptions, add expenses from maintenance and miscellaneous categories. Implementing surge protection can yield 30 to 70% reduction of these combined costs. And the investment ROI is typically less than 1 year. The savings are ongoing. They become a continuing annuity, a great investment. Data telecom surge protection. This table lists the application descriptions across the top of the chart. Examples are line pairs, phone, fax, DSL, ISDN, PoE-A, 4 to 20 milliamp current loops, RS-232 and 485, Cat5 and Cat6. Connection methods listed in column 1 on the left-hand side. Terminal screw, RJ45, RJ45 to a 110 punch down. D-sub, wire leads, 110 punch down and a 66 punch down. Mounting types listed in column 2. DIN rail, wall mount, inline, 19-inch rack, 19-inch patch panel, etc. Product images are defined in figure column 3, which are shown under the chart. See figure A through figure L. We have found this chart to be helpful in applying surge protection for data telecom applications. Other examples of data telecom products: a 1, 2, and 4 port coax devices, a 1/2 inch MPT hub mount 4 to 20 milliamp current loop device, a TSN 240/120 VAC light commercial and residential SPD, a TSN compact 2 and 3 phase AC SPD for small business and residential, a 4 phone line plus 1 coax module, and a TSN flush mount cover. This is a Mac Victor Power Network, an MVPN. It provides clean and continuous power with battery backup, offering 2 and 3 kVA sizes. Features: first, reduces operating and maintenance expenses, eliminates downtime due to software lockups, data errors, and hardware failures. Number 2, true online double conversion UPS, provides voltage and frequency regulation to support and protect mission-critical applications. Number 3, bypass switch, make before break, provides seamless power during UPS maintenance. Number 4, wall-mounted design, saves vital floor space. Number 5, integral shielded isolation transformer. Number 6, integral surge protection, 40 Ka on the input and 40 Ka on the output with EFI, RFI filtering. Number 7, it's UL 1778 second edition listed. 8, it is U.S. patented number 7408271 on August 5th, 2008. Applications: convenience stores, fast food restaurants, gas stations, point-of-sale equipment, back office electronics, customer kiosks, printers and monitors, wastewater controls, and location servers and communication racks. Power quality surge protection presentations. These presentations last 60 to 90 minutes. A presentation syllabus PhD letter. All attendants will receive a letter for continuing education using a syllabus covering the presentation topics and the total number of contact minutes of the presentation. This letter may be submitted for professional development hours, PDHs. Power quality presentation topics. Design philosophy. Surge protection devices, SPDs. Risk assessment, a SPD sizing guide. Modes of protection. System grounding guide. Concerns of SPDs integral to switchgear and panel boards. Power quality problems and solutions. Data telecom applications. Industry standards, IEEE, UL, and CUL. Single sheet specs for facility, design build, and bid specs. Other topics discussed: performance, products that deliver full surge ratings. Packaging, modular and non-modular. Quality assurance, using Six Sigma management by fax. Value, provided by using 2- and 3-tier hybrid designs. Stack tracks, low impedance surge paths. Applications, we match protection to the environment and equipment criticality. NEMA ratings, status indication, fiberglass and polycarbonate enclosures with clear covers. Surge apps are technical papers addressing specific applications. Most are a one-page document. Surge apps topics are defined by questions during our power quality presentations. These questions came from end users, specifying engineers, and our own field sales representatives. They address real issues and provide useful application information. The most read surge apps are SA001, Surge Protection, Why THOR Systems. SA004, Risk Assessment, used for sizing surge protection. SA006, Specs Define Effective Surge Protection. Requested topics are SA025, All surge protection is not equal. Next is SA038, Site Survey, Why? SA044, Cost of Poor Power Quality. These surge apps can be downloaded from www.thorsystems.us, or you can sign up to receive an email surge app once per month. A number of engineers have asked us for a single sheet specification. THOR developed 3 single sheet specifications. The first is a design build spec, listing THOR only. Second is the facility spec, providing life of the installation warranty, offering 2 alternative manufacturers. Third is the bid spec, plus 2 alternate manufacturers. The 2 alternate manufacturers are Current Technology or Liebert/Emerson/Vertiv, now ASCO. The single sheet spec defines the SPD KA and VPR ratings, 2 charts included, to assure surge performance. The UL and NEMA standards help define product value, all without sales propaganda. Multi-page specifications. Our design build and bid specs define where to place surge protection, correctly sizing surge ratings per mode and per phase. SPD series, modular versus non-modular. How to feed, i.e. bottom feed. Specification format. These specifications are open, non-proprietary, offering options, not mandates. They are Microsoft Word documents created in CSI format with selectable form fields. We list 3 manufacturers with their specified product series. First, THOR Systems, TSR and TSN series. Current Technologies, SL3 and TG series. Third, Liebert, Emerson, Vertiv, now ASCO, 570 and 520 series. The last 2 pages of the specs are engineering notes, which address terminology, industry standards, applications, connections, risk assessment-based surge guidance. We offer the service of reviewing existing specifications, suggesting changes to bring them in compliance with the latest industry standards, and specifying surge protection which provide high performance, longevity, and good value. Concerns regarding specs that mandate SPDs must be integral to switchgear and panel boards and must be provided by the switchgear manufacturer. First, collateral damage. Second, serviceability having arc flash concerns, which require the same personal protection equipment, PPE, which must be used for access to switchboard or panel board. Third, direct bus SPD failures can result in system shutdowns and corruption of existing distribution equipment. Fourth, integral SPDs are typically lower performance SPDs. 5. The customer often pays an inflated cost hidden in the electrical switchgear package. 6. Integral SPDs eliminate competition who offer higher performance, better value products. We believe the most effective means of addressing this issue is defining the reasons why surge protection should be external to the switchgear or panel boards. We are pleased to send you any or all of these specifications. A reference document, Surge Apps SA 006, specs define effective surge protection. These are 2 SPD spec sheets for the TSR modular and the TSN non-modular SPDs. Both define the general information, providing you a listing, the applications, and warranty. Electrical specifications, providing voltage configuration, recommended circuit breaker size, and SCCR for the application. Mechanical specifications provides the enclosure type, the SPD size, and input termination. Surge specifications provides kW per mode, MCOV, hybrid design, and monitoring. Product options provides surge counter, extended filter, pharmacy contacts. Features and benefits: low impedance surge paths and TPMOVs. Performance data, the let-through voltage levels. Model nomenclature, part number, and its makeup. Questions and answers. These questions have been asked during numerous presentations, coming from engineers, end users, facility managers, electrical distributors, contractors, and our own sales rep staff. The information related made the presentations more interesting and informative. We encourage reading through as they all present relative application-specific solutions. These are the THOR Systems facilities. We're located in Richmond, Virginia. We were incorporated in December 2003. We were the first surge protection manufacturer to complete UL 1449 3rd edition, a full 2 years before the mandatory compliance date. Our totally new 3rd generation products set the pace of change rather than reacting to change. You all have an open invitation to visit with us, have a power quality surge protection presentation, see our facility, our products, and their defined manufacturing processes. We believe you will find the visit to be informative and a good utilization of time. We encourage and look forward to your visit with us. These photos show our production areas. We are committed to company and product performance using Six Sigma principles, management by facts, which is an integral part of our production processes. We are focused on continuous improvement by identifying and preventing defects in product manufacturing. Dedicated workstations are set up having only the tools and inventory components required to support a specific assembly operation. Examples are multiple high-temperature soldering stations are required to heat and flow solder on a parallel heavy copper circuit boards. Committed inventory supply bins are also arranged to support individual product sets, such as the TSR modular backpan assemblies using multiple tile design, and the TSN non-modular design, which uses a single tile. We use more than 50 custom wiring assembly fixtures, which are keys to providing the correct configurations used during the production processes. Our production staff takes great pride in assuring very accurate assembly and dress-right dress specifically oriented and color-coordinated wiring, which is inspected at assigned pre-test points throughout the production processes before being moved to final testing and packaging. Production process continued. The first left-hand photo is showing final product testing stations. Each individual product must have full rated voltage applied during the testing procedures. The right-hand photo shows 8 Mac Victor Power Networks, MVPNs, being assembled. THOR's objective is to redefine product value in our marketplace, providing uncompromising performance and execution for all with whom we conduct business. This concludes our presentation. If there are any questions, we welcome you to visit our website, send us an email, or give us a call. We appreciate your time and interest. We look forward to becoming your power quality partner and source for surge protection by offering products and services that provide protection from the more obvious external to the more frequent internal transient events. Thank you for your time.